Hello everybody, and welcome to our next lecture of 6838. Today we're going to embark upon a series of two and a half lectures that cover one of the most classic topics in both theoretical and applied differential geometry. Like if you take a totally theoretical differential geometry undergraduate course over in the math department, you'd spend a lot of time on this topic, and in the applied world we'll spend a lot of time on it too because it's just that important. And that topic is computing the curvature of surfaces. So essentially our goal for these lectures is going to be to quantify how a surface deviates from flatness. So remember that a surface is a locally two-dimensional object, but essentially our last lectures that were just defining surfaces really were mostly topological in nature. We were just defining what it means to be a surface. Now in today's lecture, now that we know what it means to be a surface, we want to know how to distinguish one surface from another, and we're going to start by doing that with the most classical approach, which is by computing curvature. Curvature is exactly what it sounds like. It's a measure of bendiness, and we'll see that there are two really important notions of curvature on a two-dimensional surface embedded in 3D. Those are Gaussian curvature and mean curvature. And these two curvatures sort of quantify all the different ways that a two-dimensional surface can bend through three-dimensional space. Unsurprisingly, both of those curvatures are going to equal 0 when a surface is flat, because flat things don't have curvature. So there are all kinds of high-level questions that we can answer when we go about trying to compute curvature. So for instance, we're going to be able to use our curvature measures to distinguish at different points on a surface, by the way, this can change from place to place, between bowl-shaped surfaces like the top, parabolic surfaces like the middle, and hyperbolic surfaces like the bottom, as we see on the slide here. We're going to see that those three classes are easily distinguished by a particular measure of curvature called Gaussian curvature. On the other hand, we can also see kind of how the surface interacts with its normal vector. Like, does it bend toward or away from the normal vectors, like the first two images that we see on the top here. And we're going to see that that is largely quantified by a second notion of curvature called mean curvature. And this question of how to distinguish different types of surfaces shows up all over the place when we start analyzing geometry. So for instance, a sort of related question we could ask is, how does a surface interact with space? So here I show you a piece of origami, I would say a pretty boring piece of origami, where it's essentially just a flat sheet that I've creased a few times and then bent into space. Now, the key word here, and one that we often use informally, but rarely do we think about it formally in mathematical terms, is bent. We bent the flat surface to achieve the surface on the right. Now, in our course, when I say bend, what I'm going to mean is that I deformed that flat surface without changing its distance structure. So in particular, let's say that I'm an ant crawling along that sheet of paper. And so when the paper is bent, if the ant crawls along and it just moves along the bend, the ant cannot distinguish between the left and the right cases. So in other words, if all the ant knows how to do is to compute distances along the surface, these two surfaces are identical. Now, obviously, the way I've rendered it here, these are not identical surfaces, right? One of them is completely flat, and one of them is bent over. And so essentially, ants can't distinguish bending of surfaces. They can only distinguish stretching. And so what we're going to see is that one of our notions of curvature is largely designed to detect this style of deformation, which kind of really has to do with the interaction between the surface and the space around it. And then another one, where like maybe I just stretch out my surface like a piece of rubber, is going to be associated to a different notion of curvature. So in fact, this sort of theme of like, does the surrounding space matter, one that we originally raised in our very first lecture in 6838, is going to keep coming back over and over and over again. In particular, what we're going to show is that the surrounding space really doesn't matter for one notion of curvature called Gaussian curvature, but it does for mean curvature. And we're going to see that in a variety of different ways in both the discrete and the smooth cases. And of course, we're going to talk about many practical applications. My favorite one that I saw on the internet is that once you understand surface curvature, you can optimize the way that you eat a piece of pizza according to science. Apparently, we've all been doing it wrong. So I'll refer you guys to this article here for additional detail on this groundbreaking application of surface curvature. Now, the first thing we have to do is think about what our approach should be. How should we go about quantifying the bendiness and the stretching of surfaces that are sitting in 3D? And one way to do it that I think is kind of a reasonable approach given what we've done so far is to go back to the case of curves. So recall that we've already talked about curvature and a different notion of bendiness called torsion when we discussed the differential geometry of smooth curves. Remember that the curvature of a curve kind of is like the steering wheel direction of a car as it drives along the curve in a plane. Then the torsion is kind of how the curve lifts out of a plane. And we spent quite a bit of time very carefully defining these two notions. So what we're going to do in today's lecture is basically to leverage what we already constructed for curves and lift it to the surface case. So the way that we're going to do that intuitively is actually pretty straightforward. We're going to think about drawing curves with the restriction that the curves only can live along the surface. They can't, they're like paths of a car driving along some bendy landscape. And essentially what we're going to see is that the curvature vector of that path which is restricted to move along the surface, has certain structure that we can use to describe the surface itself rather than the path. And in fact, that's actually pretty intuitive. So for instance, let's say that I'm driving a car along a bumpy piece of terrain, right? So as I drive my car, it goes up and down and up and down. Notice that if I were a passenger in the car and I closed my eyes, I could sense the fact that my car is moving along the terrain, right? There's acceleration, which is essentially due to the fact that the ground underneath the car is changing. And that has to do with the ground. It actually doesn't have to do with my car, right? There's no way to drive along a curved landscape and not feel some force, which is due to just keeping you on the ground. And so essentially what we're going to see is that that force is roughly the curvature of the surface in a given prescribed direction. And so we're going to formalize all these notions, of course, but really that's all that's going on. Again, that if I can drive a car with constant speed along a surface, then I can sense the curvature of that surface, which is pretty cool. Okay, so we'll first recall a few notions from the last few lectures just to make sure that we all are on the same page. And then we're going to dive right into some computations, definitions, and a bunch of stuff in between. So let's get started. So, of course, the main thing that we're going to make use of today is the unit normal to a surface. Now recall that only orientable surfaces have unit normal fields globally. But even non-orientable surfaces have unit normal fields, at least locally. So we can always do this in some small patch on a surface, although computing one global field of normals may be impossible. So today we're going to think of the normal as little n, which is a function from the surface m into the unit sphere, right? And the reason I say it's from the surface into the unit sphere is that, of course, normals are unit length vectors. Okay, so essentially we've got this notation that we set up in our previous lecture, right? A normal is going to be little n. We're going to use t sub p to denote the tangent space at a particular point p. And m is going to stand for manifold, but today we're in the two-dimensional domain, so m is always going to be a two-dimensional manifold or surface. Moreover, we're not going to worry about manifolds with boundary for now. In fact, defining curvature on a boundary is a little bit of a tricky matter, and you have to decide whether it's important for a particular application or not. So this is a pretty typical thing to omit. So if you'll recall, when we talked about the analysis of plane curves, we defined a particular object called the Gauss map, which mapped every point on a plane curve to its normal vector, in this case on the circle, which is S1. Now we're going to lift the Gauss map to a surface sitting in 3D, which now is going to map to the unit sphere, which is notated S2. And then finally, as a last little bit of review here, recall that we essentially define curvature in terms of this object we call the Frenet frame, which is essentially measuring how the tangent, normal, and binormal vectors of a curve change in response to the curve deviating from flatness. So what we're going to do is leverage some of the measurements here to define curvature for a surface sitting in 3D. Now, if any of these terms is a little unfamiliar or still uncomfortable, that's okay. We're going to try and recall them as we go through today's lecture. And the great thing about having video lectures is, of course, that you can go back and watch it again and make sure that you have the right intuition. Okay, so let's get started. So as I've already mentioned, the basic object that we're going to work with today is an object called the Gauss map. Gauss, by the way, his name shows up all over the place. There's a Gauss map, there's Gaussian curvature. He's a big guy when it comes to differential geometry. So the Gauss map of an oriented surface is a map from the surface into the unit sphere, which is just giving the unit normal to every point on that oriented surface. Notice that an oriented surface, I guess, has kind of two choices of Gauss map, whether the normal point's outside or inside. We're just going to assume that somebody has oriented the surface, meaning they have chosen a normal direction n. And the convention is usually that n is pointing outward, assuming that your surface is closed and has an inside. So we're going to need one additional notion, which we've already introduced in past lectures, and that's the differential of a map. In fact, we've defined it a few different ways because we first talked about the differential of a scalar function, and then we lifted it to a differential of a more general map between spaces. So just as a tiny review, remember that if phi is a map from M into N, here both M and N can be submanifolds. Then we can define the differential d phi at a point P as follows, where essentially what we're going to do is take any curve gamma whose tangent is a given vector at that point P, and we're going to say that essentially d phi in the gamma prime direction is nothing more than the rate of change of phi as gamma walks through the curve. So again, if you're unfamiliar with this definition, I know that essentially I'm skipping over it a little bit in the most general case. I refer you to the course notes or to some of the previous lectures to get an intuition for what this D object is doing. But D here really just stands for derivative. This is just a glorified way to multiply by the Jacobian matrix of a map. So the first thing that we're going to do is actually compute the differential of this map from the surface into the unit sphere. Notice the unit sphere is actually a manifold, right? The unit sphere is just a ball. So it makes perfect sense to compute dn at a point P. And this object has a name. This is called the shape operator. Okay, so we're going to draw a little bit of a schematic, and then we're going to prove a nice little lemma, which is going to be convenient for the remainder of today's lecture. So let's hide our slide in the corner here and get started with a little bit of a computation. So first, let me draw a bit of a picture just to recall what's going on. We're going to see a lot of tori in today's lecture because honestly, that is the only oriented surface without a boundary that your instructor knows how to draw. Okay, so let's go ahead and do that. So here is a torus. You can make it a double torus by putting two of these things there. And remember that, again, the normal map, we're going to use little n. By the way, I'm going to use big N and big T for like the normals and tangents of curves. I'm going to use little n and maybe little t for normals and tangents on surfaces. We'll see that big N and little n are going to be different. It's pretty rare that the tangents are different, but that's okay. So anyway, right, so our Gauss map goes from our surface into the unit sphere, which is notated S2. By the way, this is a piece of notation that always trips people up. If you have the unit sphere in 3D, right, so this is sitting in R3, then it's notated S2. By the way, I guess these axes should be right at the center of the sphere, but whatever. And essentially the reason for that is that it is a two-dimensional surface, right? It's intrinsically 2D, even if it's sitting in 3D. Right? So in general, you have like Sn minus 1 sits in Rn. Right? So this is like R3 here. And remember that essentially all n does is maps every point to its normal. Okay? Whew. So now the question is, what is this object dn? So what does it mean to differentiate the normal vector? So remember that the normal is perpendicular to the surface like that. And essentially, if we want to differentiate dn, we're going to take a point in the tangent plane to our surface. Remember, our surface is called cursive M. And we're going to see how the normal vector changes as I drive along the surface in a particular direction. Okay, so let's say that we have a particular direction in the tangent plane, and we're going to call it v. All right, so remember that we're going to notate, if our point here is P, we'll say that we're going to take V to be in the tangent plane at P of our surface M. Hopefully this notation is becoming a little more comfortable as we continue in this course. All right, so remember what it means to compute the differential. We take any curve along our surface, in this case, that goes through the point P at time 0 with velocity v, and then we look at what happens to our map. So now let's fill that in some mathematical notation, okay? So in particular, we're going to say, take a curve, gamma, and maybe we'll make it, no, I don't think we need to make it parametrized by arc length just yet. We're going to take just a general curve, gamma of t, and really it doesn't have to go on forever. It can just go on from some little itty-bitty interval. But the key thing is that it's no longer just a curve in 3D. It's going to be restricted to moving along our surface, right? That's the key part here. Okay? And we're going to endow our curve with two properties. First, we're going to say at time 0, our curve is going through the point P. And at time 0, our curve has velocity v. Okay? So our curve is some, car driving along our surface, and it goes through P kind of like that. And notice that the tangent agrees at P with the vector I've drawn, which is v. Okay, so essentially, what are we trying to do? Well, we're trying to understand what it means to differentiate the normal vector at point P in the direction v. And just by definition, one way that we can do that is by saying, okay, well, we have this map n, which goes from the surface to normal vectors. And we have a map gamma, which goes from times into the surface. So it makes sense to compose the maps like this. And essentially, but just by definition, dn of v is equal to n composed with gamma prime at 0. So let's make sure that we know how to interpret this expression. Essentially what it's saying is that the rate of change of the normal in the v direction can be sensed by driving a car along my surface through point P, and the car, as it's driving along the surface, is collecting normal vectors and just computing the rate of change of the normal vector as it passes through P. Okay? One thing that I guess we haven't checked carefully in this course is to make sure this is well defined. There's a little bit of a homework problem here, which is to say, if I chose a second curve, gamma, whose tangent also was v and went through P, that I get the same quantity. That's just a simple calculus exercise. I'll let you check that at home if you don't trust me. So essentially, now we know something about how to define dn at P of v. And we can just make use of one additional lemma that we already proved, which is the following. Now recall that the normal vector, just by definition, is always unit length, right? So if I look at n composed with gamma, you can think of this as a function of t, namely because it is, right? So if I look at the 2 norm of this vector, it is identically equal to 1. So as the car drives along the surface, it just always finds unit length normal vectors as it drives along. That's not terribly surprising. But if you'll recall, we proved when we were talking about curvature of curves, a very useful little lemma, which was to say if I draw a curve of unit length vectors, then the velocity of that curve is necessarily orthogonal to the curve itself, right? So in other words, what we've shown is that because n is constantly unit length, just recalling the same proposition that we proved for computing the curvature of curves, that this thing had better be orthogonal to n. Okay, well, if a vector is orthogonal to the normal of our surface, I guess at P maybe to be precise, what do we know? Well, the space of everything orthogonal to the normal vector is by definition the tangent space. So in other words, what we just showed is that dn at P of v is inside of the tangent space at P of our surface M. So this is kind of an interesting thing. Essentially, if we want to complete the right-hand side, the little question marks in our expression up here, what we just showed is that the differential of the normal map, or of the Gauss map, goes from the tangent plane of our surface, a definition, into the tangent plane of the surface. So we never actually need normal vector information to differentiate the normal vector. This is, I don't know, surprising, not surprising, depending on how you think about it, but it's certainly an interesting and useful fact, and it's a really basic one that we're going to leverage throughout today's lecture. So with that, let's clear out a little bit of space and keep going here. Okay. So now we have at least figured out what space the derivative of the normal vector lives in. Our next goal is to start using the derivative of the normal vector to actually measure interesting things about the geometry of a surface, or at least to interpret this object, the shape operator dn, in an interesting and useful way. And so we're going to do that by defining an extremely famous object, which is called the second fundamental form. Now, probably I should have put a subscript next to the 2, by the way, to make it like 2 sub p, but hopefully you guys can all read with me for today rather than revising my slides live. So the second fundamental form at a point P does a very particular thing. It is a function of 2 different tangent vectors, v and w, and it inputs those 2 vectors and outputs the thing that I've highlighted here in green, minus v dot the shape operator at P evaluated at W. So in differential geometry phrases, if you take a more advanced geometry course, we'll say that essentially there's a very easy relationship between the second fundamental form and the shape operator dn. In fact, if you have one, you have the other. Essentially, they're just related by dot products, right? So remember that the shape operator, which is just dn sub p, it's on this slide too. What does it do? It inputs one tangent vector and outputs another tangent vector, whereas the second fundamental form inputs 2 tangent vectors and outputs a scalar. But you can sort of reconstruct one from the other. So for example, here I'm giving the formula for how to write the second fundamental form in terms of the shape operator. You can go the reverse direction too by kind of plugging in a basis for v and w and enumerating all the possible things you could do. In any event, we like the second fundamental form because it's a really fundamental object in differential geometry and actually encodes some really interesting geometric information. So our next task in lecture today is to figure out precisely what that information is. Because if we look at the formula on the slide, there are a few kind of fishy aspects here. Like, why is there a minus sign? Why do we go to all this work rather than just working with dn directly? So now let me show you. In particular, what I'm going to do is I'm going to take a unit vector, capital T here, and I'm going to put it into the second fundamental form twice. So I'm going to put the same argument in both slots. And we're going to see that this actually has a really nice interpretation. Okay, so let's do that. So in particular, we're going to keep using the same trick in today's lecture, which is anytime we talk about vectors like these, this capital T here. So first of all, I'm going to think of capital T as in the tangent space at a point P of my surface. Notice that I used capital T. I apologize, there's a little bit of ambiguity between the T on the left and the T on the right, but hopefully you can read with me here. When I use capital letters, I'm usually referring to curves, and in fact, let's do exactly that. So let's take a curve gamma, and I'm going to use S, which goes from minus epsilon to epsilon into our surface. And the reason I'm using S is that I'm going to think of gamma as being parametrized by arc length, just for convenience. Okay, and now I'm going to have a few properties. First of all, I want my curve gamma to pass through my point P at time 0. So we're going to say that gamma of 0 is equal to P. And just like we had before, we're going to want our tangent vector to our curve to agree with capital T. Gamma prime of 0 is equal to capital T. I accidentally erased our schematic, but I think you guys could all draw what's going on in this picture now. If you can't, you should pause for a minute and think about it. So again, just kind of by definition here, what do we know? Well, we do know that the tangent plane, or the tangent vector to our curve rather, gamma prime of S is in T gamma of s of m, right? That's just by definition, because essentially this object here is a velocity vector, and remember we defined the tangent plane to a surface to be the collection of velocity vectors of curves through a given point. Okay, so one thing that we know about tangent vectors is that they are perpendicular to normal vectors. Yeah? So in particular, we know the following dot product. We know that gamma prime of s dot product with the normal vector at gamma of s is always going to be equal to 0 for all s, right? And that's just a statement of the fact that gamma prime is in the tangent plane and n is the normal vector. And just by definition, these things are perpendicular to one another. So now we're going to use the product rule and differentiate both sides with respect to s. Okay? I'm also going to swap the left and the right-hand sides. So when I differentiate, d over ds here, well, the derivative of 0 remains 0. That part is easy. And now let's differentiate this expression here. So first of all, so remember that gamma prime here, this is really capital T of s by definition here. And what is the derivative of the unit tangent? Well, if you recall from our previous lecture on the differential geometry of curves, if I differentiate the unit tangent with respect to arc length, what I get is the curvature normal of my curve, evaluated at s, dot product with n of gamma of s, here I'm doing the product rule, plus, okay, we have t of s, dot product d over ds of this expression here. But if you think about it, well, what is that? That is exactly dn evaluated at gamma of s of gamma prime of s, just by definition. Okay? Whew. So let's take a step back and look at this expression a bit. So first of all, we know that gamma prime here, this is t again. So this entire expression, notice it's t dot product dn of t. So in particular, this is like the second fundamental form evaluated at t comma t. With a minus sign in front of it because there's a plus here. Okay, so what did we show? What we showed is the following. If I just basically move the second term to the other side of the equation, we showed that if we substitute in the second fundamental form evaluated at the same tangent vector twice, then we get the curvature normal of the curve dot product of the normal of the surface. Now, this is a little bit tricky to think about. Notice that there's two n's in this expression, and it's really easy to confuse the two. So this n here, this is just the second derivative of our curve parametrized by arc length. It comes from the curve, not the surface. It doesn't even know there is a surface. Whereas this little n, this is the normal to the surface, right? So this is the surface normal. Sorry, that was a tautological sentence there. Okay. So essentially, there's actually two different normals that are interacting here, and that's what the second fundamental form is trying to tell us about. So let's think about it this way. So let's say that I had a totally flat surface, namely the plane. There it is. Well, I can still draw, if I have a point P, I can draw a curve through P like that has curvature in the curve sense of the word curvature, right? So in other words, even though the plane here is flat, if I have my little car and he's driving along the car can still be turning its steering wheel, and that curve can have curvature, right? And so that curvature vector is kappa n. Now, what is this little n? Well, on the blackboard, it's a vector pointing straight out of the board, right? So what is this dot product going to be in that case? Well, this is actually going to be, this is where things get confusing, right? So kappa n, again, is the curvature of the curve gamma. It is not the curvature of the surface. And in this case, since the curve gamma is in the plane, this dot product would equal 0. Do you see that? Because little n here is the normal to the surface, and big N is the normal to the curve, which only knows about the plane geometry. So let's see if we can develop an intuition more generally, okay? So let's again return to my favorite surface here, which is the torus. And we have some car that's driving along the torus. You know, maybe it's doing all kinds of crazy path, like that. So if we call this curve gamma of s, we could ask the question of, if I'm a passenger inside of the car, what are all the forces that I can feel? And those forces can be essentially separated into many different components. So in particular, if I am a person driving the car, well, one thing that I could do is just jam on the accelerator of the car so that essentially it's tracing out this curve, but it's tracing it out faster and faster and faster, right? So even if my car is driving in a straight line, I can still feel acceleration just by speeding up as I drive along that straight line. But we're pretty sure that that acceleration is not interesting from a geometry perspective. That was just how I chose to trace out a curve. Yeah? And so the way that we get rid of that type of acceleration is by assuming that our curve is parametrized by arc length. So now we have a pretty sane driver, right? Our driver is driving with constant speed, so we don't feel acceleration in the forward tangent direction. But that's not to say that we don't still feel acceleration. The driver of the car has two different ways that they can still make you sway around in your seat of the car. And here are those two ways. First of all, right, I didn't tell you what curve I'm drawing along my donut surface. It could be that as I drive along the donut, I am doing donuts or whatever. My car is swiveling back and forth. I'm turning the steering wheel left and right. So even on like a relatively innocuous nearly flat surface, I can still make you have a bumpy ride by turning the steering wheel to my car many, many times. That still is not an interesting piece of geometry for the surface. It is interesting for the geometry of the curve, right? That's what's making this curve look so wiggly. But it's not telling us about the torus that's sitting underneath the car. But then there's a third source of acceleration. There's a third force that passengers in your car feel. And that is the force due to geometry. And that's kind of a funny phrase, but that's really what I mean. The force due to geometry is the fact that even if I don't turn the steering wheel, and even if I drive straight and I don't hit the accelerator, the passengers in the car still feel the fact that maybe I'm driving along a rolling hill. The car is moving up and down. Or in this case, the car is circling around a donut. And it's that third thing which is sensed by the second fundamental form. Now, how do I know that? How did I come to that conclusion? Well, take a look. So there's essentially two pieces in this expression. One of them is this kappa n term. And this is the total force on the passengers in your car. That includes the force of turning the steering wheel and the force due to geometry. Now, since I said parametrized by arc length, there is not a force due to just accelerating along the curve. But then I took kappa n, and I computed its dot product with the surface normal. Okay, so if you think about it, when I turn my steering wheel, I can't make a car go into the ground, right? I can only move it tangentially. And so if I take the normal component of the force experienced by the people in the car, that is precisely the force that you're experiencing due to the geometry that you're driving along, as opposed to just turns in the steering wheel. So in other words, we can take this kappa n and we can further divide it into two components. One component parallel to the surface normal, and another component that's in the tangent plane. The tangent plane component is really like what makes the curve interesting as it moves along the surface. That's the steering wheel part. And the part that's parallel to little n here, that is the part that is due to geometry. So that is our nice intuition for what it means to compute the second fundamental form. Again, if I put the same tangent vector in twice, you're sensing the acceleration due to geometry. Okay, so let's erase the board and I'll show you a nicer picture of what that feels like. Okay, so again, we essentially have provided a nice intuition for what it means to evaluate the second fundamental form at the same point t twice. In fact, incidentally, I think this has a name. It's like Moisnier's theorem. My French is not very good. But now here's a better picture of exactly the same phenomenon I already talked about. So Essentially, we can take the curvature vector of our curve drawing along the surface and essentially take its acceleration and divide it into two pieces. The first one is the acceleration in the normal to the surface direction, which again is the acceleration due to geometry. The second term, incidentally, what's left, we call geodesic curvature. And this is a property of the curve rather than of the surface, right? So the geodesic curvature of a curve is the component of its curvature direction in the tangent plane. And again, it's basically just measuring how the driver of the car driving along the surface is exacting curvature on the curve by turning the steering wheel. So for my next trick, for the next thing we're going to do in this class, we're going to prove a really useful property of the second fundamental form, which is that it is symmetric. Namely, that if I take two tangent vectors v and w, I can evaluate the second fundamental form in either order, v comma w or w comma v, and get the same number back out. I'll be honest, well, I'm able to draw some really nice pictures for what everything else we've proved so far is telling us about life. I actually have had a little bit of trouble interpreting this particular statement mathematically, and I would love if one of the students in this course could draw a really nice schematic that visually convinces us that this property should be true. But we're going to just derive it using machinery from calculus, and without as much geometric reasoning, which is a bit of a shame. So anyway, that's okay. Let's do that anyway because we're going to need it for some of our calculations. Okay, so in particular, we're going to have our surface. Let's call our surface M here, as always here. So here's our surface. And I'm only going to worry about a patch of our surface because remember that all of our curvature calculations are local anyway. So remember the definition of a surface is that around every single point, like here's our point P, there's some neighborhood with a parameterization from the plane. So let's draw our local neighborhood and our parameterization. So I'm going to say that we have some map phi that goes from the two-dimensional plane into our surface M. At the very least, maybe the origin gets mapped to P and some small neighborhood gets mapped to this neighborhood here. We'll be outside of that neighborhood is not going to matter. We're just going to compute some small derivatives. And just for convenience, let's label our axes x1 and x2. So really the direction of the axis would be E subscript 1 and E subscript 2, and their coefficients would be x superscript 1 and x superscript 2. By the way, hopefully you guys all are getting the pattern by now that this is not x squared, this is x superscript 2. Okay, so in any event, our goal is to prove this symmetry property on the upper right. And let's see if we can go about doing that. So first of all, now that we have a map phi, what happens if we differentiate phi in the x1 or the x2 directions? Well, if I just take a slice through our two-dimensional plane here, it's essentially tracing out a curve on the surface, right? So in particular, what do we know? We know that d phi dx1 and d phi dx2 are both tangent vectors to our surface. So we can write two different facts which are useful about life. So remember that little n is the normal. So we know that the normal dot product d phi dx1 is 0, where these are evaluated at the same place, of course. I'm going to be a little sloppy with notation. And we know that the normal dot product d phi dx2 is also identically equal to 0. So we're going to keep essentially using the same like 3 math tricks over and over and over again in the next few lectures. In particular, we'll have some like orthogonality relationship, and we're just going to differentiate the heck out of it. Yeah. So in particular, one thing that we can do is we can differentiate relationship 1 here with respect to x2. So let's do that. So again, what we're going to do is differentiate 1 with respect to the second coordinate, x2. All right, so then what are we going to get? Well, the derivative of 0 is 0. We're getting really good at that, yeah? So we get 0 on one side. Let me swap the left to the right. And what do we get on the right-hand side? Well, we know that this is equal to d over dx2 of n dot d phi dx1, like that. So now let's apply the product rule, and we're going to see that we get two different terms here. Well, the first one is equal to the derivative of n with respect to x2 dot product d phi dx1. So that's like this, dn dx2 dot product d phi dx1. Now we can add a second term to that, where we apply the derivative to the second part. So we're going to get plus n dot. Now we have two derivatives, right? So we're going to d squared phi, and one of our derivatives is with respect to x1, and one of them is with respect to x2. And remember, the derivatives commute, so I can put either guy first. So I'm going to just write dx1 dx2. We'll keep things in order. Okay, so we differentiated formula 1 here with respect to x2. What do you think the next thing is going to be? Well, I wrote both of these expressions here. One thing we could do is differentiate 2 with respect to x1. So we'll say differentiate 2 with respect to x1. It's supposed to be 1 and not an exclamation point. And then what do we get? Well, just following exactly the same pattern, we know 0 is equal to d over dx1 of the normal dot product d phi dx2, right? That's expression 2 here. And again, just by the same product rule, nothing too exciting here happens. It's just the roles of x1 and x2 swap. Yeah? So now we have dn dx1 dot d phi dx2 plus n dot. And this is the same mixed partial that we had in the previous expression. Uh-oh. d squared phi dx1 dx2. Okay, so we have two different expressions, both of which equal to 0. So the one thing that we can do is subtract them from one another. And what do we get? So if we combine these two expressions, then we get by subtraction that, let's see here, dn dx2 dot d phi dx1 minus dn dx1 dot product d phi dx2, that this difference is equal to 0. So I just got this expression by subtracting these two guys. So in other words, these two terms are equal to each other. So that's pretty cool. Essentially, it's kind of some interesting symmetry here. I can swap derivatives with respect to x1 and x2 when I'm dot producting between derivatives of phi and derivatives of the normal. Okay, so why did I go to all that work? That seems like an awful lot of work. Well, now let's see if we can interpret these vectors in a nice way, okay? So in general here, maybe we give a name to these different tangent vectors, okay? So maybe we call, so remember that when we differentiate phi, we get tangents, yeah? So maybe we'll say, I don't know, we'll make tangent T1 is going to be equal to d phi dx1, and we'll have tangent T2 is equal to d phi dx2. 2, like that. All right. So what did we do here? Well, if we look closely, this is the derivative of the normal vector in the x2 direction, dot product with T1. Yeah? So this thing essentially is the same as saying, okay, well, maybe let's go ahead and plug in rather than getting ahead of myself. So I'm going to swap the order of these two terms. This is d phi dx1, which is T1, dot product. And this is the derivative of the normal, dn. I'm going to omit the subscript for now because I've been a little sloppy about where we're evaluating things. But, okay, it's in the x2 direction. So it's like that. Minus T2 dot product dn of T1. So these are just equivalent ways to write the same expression. All I did here was define the t's and recall that dn in a particular direction is nothing more than differentiating the normal in that direction, which is what we wrote here. Okay, and obviously I can move things to the other side, right? So this is the same as saying that t1 dot dn of t2 is equal to t2 dot dn of t1. Okay, so now essentially we've proven some version of our symmetry relationship, but only for two particular vectors, right? So in particular, by multiplying both sides by -1 here, essentially what we've shown is what? We've shown that the second fundamental form of t1, t2 is equal to the second fundamental form of t2, comma, t1. Now, it's also really obviously true that, if I put in the same thing twice, I can swap the order because they're the same, right? So really, what we can say is that the second fundamental form of ti, tj is equal to the second fundamental form of tj, ti for all I, j. And that's just because when I is equal to j, this is kind of a boring thing to say. And of course, I and j here only index between 1 and 2. Okay. So we're almost there, right? Here we have an expression for general v and w, and we've shown it for essentially t1 and t2, and now we just have to make sure that these are the same. But one thing that you can check quite easily is that the second fundamental form here is bilinear, meaning that it is linear in both of its elements. Okay, so in particular, let's say that I have a general VW. Well, one thing that I can do is, by definition of a parametrization, we know that T1 and T2 span the tangent plane, right? So in particular, I can write V in the T coordinates. So I can say, okay, so this is really equal to like V1 T1 plus V2 T2. If I were being really slick with my Einstein notation, I guess I could write this in a nicer way. And similarly, this is W1 T1 plus W2 T2. Okay, but by bilinearity, this is really equal to the sum of V over I and J of VI WJ, second fundamental form of TI TJ. Okay, but now we can apply the fact that we proved up here to say, well, this is the same as the sum over I and J of VI WJ, second fundamental form of TJ TI. And kind of working all these steps backward, again by bilinearity, we get that this is the second fundamental form of W comma V. I had an undergrad math professor many years ago that used to give us a hard time for victory marks at the end of proofs. He said we need to write QED, but I'm going to write a victory mark because I'm feeling good today. Okay, so essentially what did we do? We showed at the end of the day the second fundamental form for any pair of tangent vectors V and W has this nice symmetry property that I can put V and W in either order and get the same thing. And again, remember that, I guess we've erased it from our slide here, but remember that our original definition of the second fundamental form, right, which is as follows. It's minus V dot dn at W. In this form here, it's really not clear that the second fundamental form should be symmetric, right? Somehow V and W are being used in very different ways, right? W is the direction that we're differentiating the normal, and V is the dot product direction. But somehow, when we swap the roles of V and W, we get the same number. Now, one thing that we could do is we can define a matrix, L, whose elements are going to be the second fundamental form in our Ti, Tj basis. And now what we know is that this matrix is symmetric. And symmetric matrices are really nice. In particular, they have eigenvalues and eigenvectors, which we're going to use in just a second to define really useful notions of curvature, and that's going to get us to the definitions that we really wanted. Okay, so I've made a mess of the screen. Let's do some erasing and then continue. Okay, so we can actually make a really useful definition here that's going to help us and guide us a little bit throughout our remaining discussion of smooth surface curvature. So we can think of drawing a little circle around a particular point on a surface and measuring its curvature as a function of angle. So let me draw you a picture of what that means. So here I've got our favorite bendy surface M. Right, there's a M. And as always, I have some point and a tangent plane at that point. Okay, so now what am I going to do? Well, I can draw a little unit circle, like a little clock face, around my point P. And I can parameterize this thing with respect to angle, okay? So maybe I choose an orthogonal basis, like here's E1 and E2, and we're going to take E1 and E2 to be an orthonormal basis for my tangent space at point P. Well, then I can essentially define an arbitrary angle theta, a tangent direction in an arbitrary angle theta by just kind of writing, some vector, I don't know, maybe v theta is equal to, well, I could write E1 cosine theta plus E2 sine theta, like that. So this is just an arbitrary unit vector pointing out from P. So this is like drawing a little clock face around P. Well, one thing I could do is essentially write a little curvature function as a function of angle. I can say, okay, well, I am going to look at this function kappa sub theta, where I put v theta into the second fundamental form twice. Okay, so what am I doing if I think about kappa theta? Essentially, I'm standing at some point on a surface, and I'm pointing my toes in the theta direction. So now I can spin around. I'll do it for the camera here. And as I spin around and I look at my toes, the surface is like bending maybe down or up as a function of theta, right? So as I turn around, curvature is bending downward and upward. And essentially, I can view curvature as a function of what direction my toes are pointing. If I do that, then there's going to be some direction I look where the surface is bending the most, or maybe even the curvature is the most negative. It's like bending away the most. And there's going to be some other direction where the curvature is bending up the most, and that is the direction where the curvature is the most positive. Those two directions have names. They're called principal directions, and their associated curvatures are called principal curvatures. So these are defined on the slide here, right? So we have kappa min and kappa max, where essentially these are the surface curvature that are minimized and maximized in any unit tangent direction, right? That's what this optimization problem is trying to do. So if you look at the image on the bottom here, this is an example of principal curvatures. People compute principal curvatures all over the place when they work with 3D surfaces. Essentially, they tend to point in interesting directions along the surface. So this model here is a famous 3D model. I think it's fertility.obj. And you can see that one of the principal curvature directions, for example, on the kind of tube-like part of the surface, is wrapping around the tube, and the other one up and down. Maybe I'll draw that a little bit better. So here is a cylinder. Okay, so in one direction of our cylinder, like up, or actually down, right? It turns out that principal directions are only known up to sine. Well, the curvature is 0, right? A cylinder is flat along this cylinder. And it's the most bendy as I move around the cylinder. Yeah, so like this would be, I guess, kappa max and kappa min, or vice versa. I always get the two confused. It kind of depends which direction you choose for your normal. Or similarly, if you have, a torus, then, maybe one of the principal curvatures kind of goes around like that, and the other one, might go around the circle. So principal curvatures are nice ways to kind of visualize locally the main directions in which the surface is bending. That's what we're showing here. And there are so many different ways to compute them. Remember that our second fundamental form is bilinear, right? Meaning that actually we only really need to know 4 different quantities, 2 of E1, E1, 2 of E1, E2, 2 of E2, E1, which is the same, and 2 of E2, E2, right? That symmetric matrix. So because of that, we can actually write curvature as a function of theta in this really tidy way. So let's say that rather than just choosing any old orthonormal basis, we actually compute the eigenvectors of the second fundamental form, and we define E1 and E2 to be those ones corresponding to the maximum or minimum eigenvalues, right? So, maybe E1 is the direction of kappa max, and E2 is, oops, I've got them backward. So we'll make that E2, and we'll make E1 the direction of kappa min. Then it turns out we get this particularly nice expression for curvature as a function of theta. This is somehow extremely profound and extremely boring all at the same time. The profound aspect here is just that, somehow I expect that surface curvature can be like this extremely complicated thing. Like, depending on where I point my toes, maybe the curvature varies widely as a function of theta, like my surface somehow ruffles in and out. But it turns out that can't happen, right? All I need to know are 2 values, kappa min and kappa max, and that's basically all that we need. And essentially, those 2 values are the curvature that are in the eigenvector directions of the matrix whose elements are just T of EI, EJ, okay? I've been a little bit informal about this. If you go through the course notes, you'll see it in a little more detail. But the basic point here is that there's a 2x2 matrix where I put in an arbitrary orthonormal basis and get 4 different values. This matrix we just showed on the previous slide is symmetric, which means it has eigenvectors. And those eigenvectors are going to be the direction of maximum and minimum curvature, which are called the principal directions and are illustrated here. And if we take E1 and E2 to be those principal directions, which we can do, they're 2 different tangent directions, they have to be orthogonal by symmetry, then what we get is this really nice expression for directional curvature in terms of just kappa min and kappa max. This is just a statement about linear algebra. It's nothing super deep. But it is kind of interesting that essentially the curvature in any direction around a point is really just determined by 2 different values. Now, there's so many different ways to visualize this. My colleague Keenan at CMU has another nice visualization involving, if I take circles that just barely touch the surface, so osculating circles to the surface, then somehow 1 over the 2 principal curvature is like the biggest circle I can get to touch the surface and the smallest one, and those 2 directions appear orthogonally to one another. Now, there are numbers that we derive from these principal curvatures, right, like kappa min and kappa max, which are the really famous measures of curvature that we care about in differential geometry. And those values are big K and big H. Big K stands, I'm noticing that I forgot to write it on the slide here, big K is called Gaussian curvature. And it's equal to the product of kappa max times kappa min, or equivalently, it's equal to the determinant of the second fundamental form. One really critical assumption when I define determinant is to make sure that my basis is orthonormal when I do that. One thing you can check is that for any orthonormal basis, I'll get the same determinant for this matrix here. And then we've got H, which is called the mean curvature. And H is just the average of kappa min and kappa max. Or equivalently, this is kind of like 1/2 the trace of the second fundamental form. Remember that trace is the sum of eigenvalues, determinant is the product of eigenvalues, which is how you get from right-hand side to the left-hand side here. And these are the most famous ways to measure curvature at a point on a surface. And it turns out that there are all kinds of different ways to interpret these quantities. They're used a lot, for example, in computer-aided design to evaluate the smoothness of a 3D model, and so on. So Gaussian curvature, we're going to see, is kind of measuring how a surface pops in and out. Mean curvature is essentially measuring how a surface interacts with its unit normal. And there are many different ways to see that. So, for example, one alternative expression that we're not going to derive in today's lecture, but is not a terribly difficult corollary of this expression here for kappa sub theta, is that the mean curvature is also equal to truly the mean curvature of kappa theta as I just move in a complete circle. So rather than just being the mean of the principal curvatures, it is also equal to the mean interpreted as an integral over the whole set of angles from 0 to 2 pi. Surfaces with minimal mean curvature are called minimal surfaces. They have all kinds of cool properties. For example, bubbles, things that minimize area, actually are called minimal surfaces, and we're going to see that they can be obtained by flowing along the mean curvature weighted normal. We'll see that in a little supplemental lecture that I'll add to this one. But the really famous measure of curvature to begin with is something called Gaussian curvature. Remember, that's this first one here, big K. And Gaussian curvature has really intuitive explanations. So Gaussian curvature can be used to distinguish between hyperbolic and parabolic parts of our surface, or I guess elliptic, like what we see on the top here. So an elliptic surface is one that's kind of bowl-shaped. The bowl can face up or face down, right? I could take the second column here and the first one and obtain them by just rigidly flipping them upside down. So from an intrinsic perspective, they're the same. And one nice property that's pretty easy to see is that if my surface is elliptic, so it's bowl-shaped, that is the same as saying that the Gaussian curvature is positive. Why is that? Well, essentially, an elliptic surface, that means that kappa max times kappa min is positive, so kappa max and kappa min have the same sign, right? So in other words, if I'm standing at a point and my point is elliptic, what that means is no matter where I point my toes, the surface is bending the same way, right? Because this is the minimum, maximum possible curvature in any direction. So if my surface is hyperbolic, that is like having negative Gauss curvature. I can never draw hyperbolic surfaces, but that's like the last row here. So a hyperbolic surface is one that is saddle-shaped, right? So in other words, if I'm standing right at that peak of that saddle, right, if I point my toes in one direction, the saddle faces downward. If I point my toes in the other direction, the saddle curves upward. And so kappa min and kappa max are opposite sign, which is what leads big K to be a negative value. And then finally, right in between those are points that are parabolic. And this are points where Gaussian curvature is equal to 0. So parabolic points are kind of like the first two things in the middle row here, where one direction is just flat, and then the other direction might be curved, right? Because if big K is equal to 0, then either K min or K max is equal to 0. So one direction along my surface is just flat. Okay, so Gaussian curvature is a really nice measure. Remember that this is a function of where you are on the surface, right? So every point P has a different Gaussian curvature and a different mean curvature, right? A surface could be saddle-shaped over here and then kind of curve out and have a bowl-shaped segment somewhere else. That's totally normal, and indeed is what makes computing curvature so interesting, right? They're functions along surfaces. They're not just property of the entire surface in one shot. In fact, constant curvature surfaces is one very small set of surfaces. They include things like a sphere and a particular type of saddle. Okay, so there's so many different formulas for curvature out there, and in the course notes I've listed a ton of them. We're not going to prove them in this course. If you took a theoretical differential geometry, you would prove many of them. So for example, one nice formula that I think is kind of fun to think about is for Gaussian curvature, and it's what I show on the slide here. In fact, I've given you two different formulas for Gaussian curvature, and essentially what they're doing is they're saying that Gaussian curvature is kind of measuring something about a circle drawn on the surface relative to a circle drawn on the plane. Yeah, so for, in particular, like C of R here might be the circumference of a circle where I look at all points that are geodesic distance R from the center point. Right, so in other words, I walk along the surface with like a piece of string tied to my center point, and the piece of string has length R, and now I draw a loop, a tiny little loop around my center point, and I compare that to just 2 pi r, which is the circumference of a flat circle. And what we'll see is that Gaussian curvature tells you something about the comparison between the length of the circumference of the circle drawn on the surface to the circumference of the corresponding circle drawn on a plane. So for instance, if I have a surface that's very ruffled, then one thing that you can sort of convince yourself in your head is that you'll end up with a lot of circumference because it's bumping up and down. So in other words, I can never draw pictures of this. I'm about to fail at it. If I have a center point like this, and a very ruffled surface, so it kind of goes like that. It's like taking cosine and then looping it around the central point. This is a very negatively curved surface. And you can see that because if I take a piece of string of length r, and now I just look at the locus of all points that are distance r away from mine, so it kind of traces this curve like that. It's a very long curve because the surface is ruffled over itself a lot. Whereas like on a positively curved surface, it's actually shorter, which is kind of cool. So for instance, now if I have a very tight bowl-shaped surface like that, you know, and I look at some point here, you know, if I draw a, if I take a piece of string of length r, and now I draw a loop, you'll see that the circumference of that loop gets smaller and smaller and smaller as I make my surface pointier. That is, as I make the Gaussian curvature more and more positive. So anyway, I encourage you guys to just spend some time on the internet reading about different formulas for mean and Gauss curvature. There's a ton of them. In a supplemental video, we're going to show one particularly important one for mean curvature involving the first variation of surface area. But that's an involved calculation, so I'm going to separate it out from our discussion here. There's also a really important uniqueness result, which we're not going to be able to prove in this course. And that is that if we know the first and second fundamental forms of a surface, we can determine the surface up to rigid motion. Now, I didn't actually define the first fundamental form, so this is not really a fair theorem to state to all of you guys. The second fundamental form was the one that we worked with quite a bit. The first fundamental form is actually even easier. So the first fundamental form is just a dot product. So it's I of v comma w is equal to v dot w. So the basic idea here is that if I have some region on the plane, and at every point in that region, I get two different 2x2 matrices, the first and the second fundamental form of not the plane, that would be boring, but rather some unknown map into a surface. So I have essentially how to compute dot products and how to compute curvature on this curved surface with some unknown map phi. Then I can actually reconstruct the geometry of the surface. However, one thing that is not true is that I can't just draw arbitrary first and fundamental forms downstairs and expect there to exist a surface with those fundamental forms. That turns out not to be the case. This is where things get a little bit different from the curve case. And in particular, you need some compatibility conditions called the Gauss-Codazzi equations, or sometimes the Gauss-Codazzi minority equations. This is an advanced topic somewhere between geometry and partial differential equations. But it does come up sometimes when we're trying to represent a surface by its curvature. And we kind of want to make sure that if I make some algorithm that's going to ignore the surface and just work with the curvature, for example, maybe I edit the curvature as a way to smooth the surface out, but then I have to embed it back in 3D. That's not necessarily possible. You have to satisfy these compatibility conditions. So more generically speaking, essentially all I'm saying is that curvature is really something that determines local surface geometry. So in other words, if I know that there is a surface with the curvature function I've prescribed on the plane, I'm basically done. But not all possible sort of functions that I could write on the plane correspond to the curvature of a surface. Anyway, I feel like I'm talking in circles, so maybe we'll end that for now, and hopefully you guys have some idea of the theory of smooth curvature. So again, the main things to take away here are that essentially we started with some surface embedded in 3D, and we asked the question of what is the curvature of a curve if it is constrained to drive along that surface. And we took that curvature vector and we divided it into a few pieces. So there's a tangential piece, which has to do with how you're turning your steering wheel as you drive along the surface. And then there's a piece that is normal to the surface, not necessarily normal to the curve. And that part has to do with the geometry of the surface. So that was this object dn, which was the differential of the Gauss map, or the shape operator. Then we used the shape operator to define the second fundamental form. And we showed that the second fundamental form is a glorified 2x2 symmetric matrix. And we also gave a nice intuition that it's essentially measuring acceleration due to curvature. Now, because it's a 2x2 matrix, it has eigenvector directions. And those eigenvector directions are the principal directions. And their associated eigenvalues are the principal curvatures. And essentially, when we multiply them together, we get Gauss curvature. When we average them, we get mean curvature. Or equivalently, this is like the determinant and the trace of the second fundamental form. And those are the two useful curvature measures that we typically try to compute on a smooth surface. I know that's a really involved story. We took a lot of different steps there, and I was very sloppy with some of them because we have limited time. So I encourage you all to review this quite a bit. Really sit back and think about these definitions and make sure they all agree with you. I think these are really critical things to get right. If we had the luxury of doing a full differential geometry class, we'd do it a lot slower, but hopefully you get some of the high-level ideas. So with that, we're going to have a little bit of a short additional lecture segment, which I'm going to record in a separate video on a different way that you can derive mean curvature by differentiating surface area. And then we're going to go forward and talk about how to approximate all these quantities on a triangulated surface.